Yes. Good job. +1. Any questions about determining formal charge? Everybody good with +1? Yeah? Know how to determine formal charge? Okay, good. Let's pick up where we left off at, outline. I believe we're at single bonds, yeah, B, starts with a single bond, CH4O. Let's see if we can get a structure here, a Lewis structure, so-called Lewis structure. Okay, charge is going to be shown on the atom. Charge should be circled. Okay, atom is charged, not if you're in any corner, and typically no brackets or anything like that for organic. Okay, charge on the atom. We'll be having lots of charges, but that's the convention that should be used. Lewis structure. Okay, Lewis structure needs to show all valence electrons, either as bonding pairs or lone pairs. So if you got to show them all, a great place to start with is how many valence electrons in this compound?
14.
Carbon has how many? 4. Each H has 1. That's 8. Oxygen?
6.
14 valence electrons. Okay. When we get done, we should have 14 valence electrons. We know H only makes 1 bond, so it's going to be on the periphery. What other atoms that we looked at only make 1 bond? Fluorine, halogens, chlorine, bromine, iodine. Okay, fluorine only 1 bond. When you get down lower, you can't have something other than standard. You can show a chlorine with multiple bonds. It ain't going to be standard, and it's using d orbitals. But very often it'll look just like fluorine with only 1 bond, most commonly. All right. Again, these guys below the second row can do some extra, uniquer, right, bonding. Okay, let's put together a structure here. The H can't be in the middle, so it can't be CHO. So pretty clearly, it's the C and the O are bonded together. This is just CH and then alphabetical. Just a formula. Okay. We want to bond together the heavy atoms. What are heavy atoms? Non-hydrogens. Called heavy atoms. Everything else is heavy atoms because hydrogen is so light. Okay? There we go. I got 2 electrons up there. All right. Recommendation, you want to put your H's on carbon. It doesn't have to be, but that's a starting recommendation, starting point. Fill the valence of carbon with your hydrogens. Okay, how many hydrogens do we have? Well, let me add, how many hydrogens can we put around this carbon? 3. That's it. You cannot put 4. Where you want to put the other H? Standard bonding for carbon, 4 bonds, 1 lone pair. Standard bonding for oxygen. Hold on, we're not done yet before we ask that question. How many valence electrons on the board? 2, 4, 6, 8, 10. Well, there should be 14.
2 lone pairs.
Yes, lone pairs. We can also ask this question. Does carbon now have an octet?
Yes.
We pretty much answered that. 3 bonds? Yes, octet. Does oxygen have an octet as shown? No, it's only got 4 electrons around it. How do you want to complete its octet? Can you add more electrons? Yes, we can add 2 lone pairs. We're anticipating standard bonding anyway. For oxygen, 2 bonds, 2 lone pairs. Now we have 14 valence electrons, and we have a good structure, which is largely governed by Octet Rule. Carbon has an octet, oxygen has an octet. Each H has a duet, 1 bond, 2 electrons in terms of the shared count. There you go, there's a good structure. Functional groups. Functional groups are particular arrangements of atoms. This is an alcohol, more specifically called methanol. Nomenclature. I mentioned yesterday in lab, and today, this afternoon, we'll give you the handout. Nomenclature by video only. The meth Meth indicating one carbon. So one carbon alcohol. Methanol. Two carbon alcohol is called what? Ethanol. On down the line. Propanol. Yes. Single bonds. Let's try the next one. C2860. Valence electrons. Anybody got it? By the way, a number of you came up with that structure on your own before class? Yeah? Yeah? Good. Question?
When we draw an alcohol structure move, when we draw the structure, would we be required to draw the H diagonally instead of like horizontally to the...
Well, we will soon start talking about bond angles. Okay? Certainly you need to know your bond angles. More commonly, this may be shown as, first off, that's very common, MEOH, because that's a methyl group OH. Okay? This is very condensed and abbreviated. We could show this as, this is good to talk about. We'll talk about these things along the way or as you ask questions. Okay? Better when you ask questions because you're thinking about it. So you ask and we can talk about it. We may show this as this. Methyl OH, it's the same thing. But here we're showing out not an abbreviation. This is a condensed sort of structure where this is just pure formula. Okay? If someone says to, just write methanol down on the paper in a condensed way, you're never going to write it like this. That's just overly generic and it has no meaning. Maybe write it like this. Gives it some structural meaning in what you can type out. Okay? This is commonly done because you can just type this if you're writing something or, this requires a drawing program or you to hand draw it or something. Very common in, we start doing line bond, we're just going to maybe put OH on the end. Okay, and the OH bond is not often shown, but it's a bond there. And I've already told you that very often lone pairs are not shown. And I drew more carbons. It says 3 carbons there instead of just 1. So these are the types of things you ask, and these are the nuances of organic chemistry that you answered by, you learned by asking. Because I can't sit here and point out every single little thing as we go along. I have to sort of respond to what you wanted to talk about and what's important for the situation. But at some point, we will certainly talk about condensed structures, and there you go. We've already sort of started doing it. Okay, over here, valence electrons. Well, we got 8, 6 is 14. What's 6 more? Was it 20?
20.
Okay, when we get done, we should have that. Okay, let's bond the heavy atoms together first. What about this? Carbon, carbon, oxygen. We can then start putting the H's. We got 6. H's on carbon first. 3, 4, 5, 6. Yeah? Carbon has an octet. Carbon has an octet. How about oxygen?
No.
No. How about 2 lone pairs? Make it standard. By the way, hopefully we haven't put more than 20. If you end up with 22 electrons, something's very wrong because we only got 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yes, everything sort of falls into place. That's a good structure. Functional groups. That's also an alcohol. What's an alcohol? It's a carbon with an OH. All right? It can be 1 carbon, it can be 2 carbons, it can be 28 carbons. All would be alcohols. The hydroxyl group, we'll look at functional groups. How'd we do? Did anybody get this or possibly some other structure? Did we do another structure? Yes, we could actually have another structure here. What if instead of the carbon-carbon we put COC? Bond the heavy atoms together that way. And then we can put the H fill the valence of carbon. What we got? Carbon has an octet, carbon has an octet. And how many valence electrons up there? Only 16, 18, 20. Now we have a standard oxygen, 2 bonds, 2 lone pairs. How about that structure?
For the bottom formula, why do you put both sets of lone pairs above the oxygen, whereas on the one on the top you put a pair above a pair below?
It doesn't matter.
Doesn't matter.
It's just me. Because there's more room on the bottom to put them. Because the bond angle's coming this way. Think about it spatially. That's below the horizontal. 2 things below the horizontal, so I put the other 2 things above the horizontal. Up there, I drew the bonds linear, so I put one above, one below. Okay. Again, that question right there could cause her headaches for 2 weeks if she didn't ask. But the answer is however you want. All right? You got to get your questions answered because a lot of times students, it's such a simple question to get you to hang up. All right? Never ask. Question?
If there are many ways to draw like that molecule, for example, how many ways would we be required to draw it?
We can't go into it right now. As we go along, you will see, again, condensed versions. Yes, multiple ways to draw compounds. All right? But it's no good for me just to have a big lecture on different ways to draw compounds because you'll just end up memorizing them. We have to just naturally work with it as we go along, but it's very important to recognize that. Okay, so, we got 2 different molecules, yeah? Is the top one an alcohol?
No.
Is it carbon with an OH? No. Bottom one's an alcohol. Anybody know the top one? It's an ether. It's actually ether with 2 dimethyl ether. Okay, functional groups. 2 different compounds. These compounds have different properties. The one on the top is a gas at room temperature. The one on the bottom is a liquid at room temperature. Same formula, different compounds. What's the relationship between these? Brothers, sisters, what? Isomers. What type of isomers are these? Because we'll see there's different types of isomers. Constitutional isomers. I bet it's written on the outline. Is it? Constitutional isomers. Definition of constitutional isomers. Different connectivity. What does that mean? Atoms are connected differently. In the top one, you have oxygen connected to 2 carbons. You have oxygen connected to 2 carbons in the bottom one. When I say connected, directly connected to 2 carbons in the bottom. No, in the bottom the oxygen is only connected to 1 carbon. Different connectivity. In the bottom you have a hydrogen connected to an oxygen. In the top there it is not connected. Same formula, different connectivity. These are constitutional isomers. Yeah? Different properties. Question?
Are resonance structures and isomers different?
Resonance structures are not isomers, no. Not isomers. Same exact compound. Resonance structures is a different way to show the same compound. And there's a lot more to that discussion. Good. Here's an important question, which some students will get to the end of the course and still don't know the answer to that question, and it's quite unfortunate. But you ask on day 2, and I think you're going to always know that. Yeah? Question?
How are they different from regular isomers, or it is?
What do you mean regular isomers? There's no such thing as a regular isomer. Any isomer has a specific type. It's a constitutional isomer. Okay? Automobile. You got trucks, bicycles, cars. They're all automobiles. They're all isomers. But what type of isomer? Constitutional isomer. Okay, double bonds. We're giving it away there. CH2O, valence electrons. CH2, carbon 4, H2, 6, 12 valence electrons. Yeah. Bond the C and the O. Yeah. We won't put the H's in. Stevens recommends on carbon, right? All right. Let's start with simple. That's our starting point. Again, always on carbon? No, not necessarily. We could have some more unique things. How many do you want to put here? 3? We need 3, right? Keep going. Hold on, we've only got 2 in the formula. Can't do that. Only 2, right? Does carbon have an octet? No.
Double bond.
I'm double. Hold on. One thing I want you to get at is we're doing it very systematically. Maybe you see we need a double bond, but down the road you may not see it, and you need a process. What's the process to get this right? So then you can go do any. How many valence electrons on the board so far? 6. We need 12 up there. All right. At this point, we want to start following Octet Rule. Fill the valence of these 2. Okay? Which is more electronegative, carbon or oxygen? Oxygen, periodic trends. Okay? Oxygen is the most greedy. It wants electrons the most. Let's fill its valence first. Otherwise, it will get mad. Be mad with us. How many? And lone pairs. Okay? Do this lone pair. How many lone pairs can we do we need to put around oxygen?
3.
We want to fill the valence. Okay? Does oxygen now have an octet? 2, 4, 6, 8. Yes. Carbon does not have an octet. Well, let's put another lone pair there. Yeah? No. 12 valence electrons. There's 12. We don't have any more lone pairs. All of our electrons are up there. Do not put more. Carbon does not have an octet. What are we going to do here? Do what?
Substitute a lone pair for a bond between carbon and oxygen.
Okay. I wouldn't call it substitute.
Replace?
No. Let me show you what we're going to do here. This is very, very important. I say very important. Everything we do is very important. All right? I don't like to do things that aren't important. What we're going to do here, very systematically, this is the language, and we're going to use an arrow here, is, okay, oxygen, we know you got an octet, we know you're happy, but your friend here is not. We're going to have to ask you to share, okay? All right? And what we're going to do is ask you, these electrons, we're going to move them in here. And that is a mechanism arrow. First one of the semester. That arrow's got to mean something. It means that we're moving these electrons in to become a bond. It does not mean that we're taking it and ending up in a lone pair here. We're not moving that lone pair over here as a lone pair. It's moving in as a bond. And it will always mean that. And if we move that in as a bond, what do we now have? Let's redraw the structure. It's as simple as that arrow. We now have what? How many lone pairs now on oxygen?
2.
Only 2, because the third one is now what? A bond, as shown by that arrow. Mechanism arrows have to mean something to you. You'll be required to show mechanism arrows on quizzes and tests. It's quite simple if you will spend the time to understand it and just make it simple. But if you never ask and never work with it, it will remain semi-confusing. Okay, and to do this. What does arrow mean? What does that arrow mean? It means the lone pair is moving in to make a bond. All right? We showed this. Now, we also have between here, I wish I left a little room, is an arrow between these two structures. A double-headed arrow, which is a resonance arrow. These are resonance structures. Because resonance structures, which I know you're going to be looking up when you get out of here, are the same structure. We'll talk more and more and more about it. All you do when you do resonance structures is move electrons. You never move atoms. Only electrons. All right? We'll do this plenty along the way. Start reading about resonance structures. Most textbooks cover resonance structures in chapter 1, 2, or 3. Okay? I only give you enough that we need to. We build and build. I actually cover resonance for test 3. Okay? Over in October. All right? By mid-October. But by the time we start covering it officially, we will have done half of it already. Pieces along the way. Okay? Question?
In the first structure, do you just
A
show,
little louder. Make sure the person in the corner can hear you.
can you just show the formal charge on the atoms in the first structure?
Very good. Let's look at charge. Yes. I was hopefully going to get there. Okay. Let's go over here now, because we're looking first for a good structure. Does oxygen have an octet? 2, 4, 6, 8. It's 2 bonds, okay? It gets to count 2 electrons, 4, 6, 8. Oxygen has an octet. We have a double bond, oxygen, and the carbon is double bond. Does carbon have an octet? 2, 4, 6, 8. Yes. Standard bonding for carbon. 4 bonds, no lone pair. There it is. Standard bonding for oxygen.
2 bonds, 2 lone
2 bonds, 2 lone pairs. A double bond is 2 bonds. We'll talk more about the nature of the double bond. It's a sigma and a pi. That's the next layer of the discussion. Structure on the right is, okay, you got 2 structures up here. I mean, for this given connectivity. Which structure do you like best, left or right? Why? Because everything has octets, and that's one of the golden rules of bonding, right? Here's a good structure. That's a carbonyl. I'm not going to talk about functional groups right now. We'll look at that in a little bit. Charge. Okay, can you really do a charge? This structure may have some validity at some point along the way. What's the charge of the carbon here? +1. Yeah? How do we do charge? Charge is done by how many electrons did this carbon bring to the dance? How many does it own itself? How many did it supply? The octet count is a shared count. We count that as 2 for carbon, 2 for carbon, 2 for carbon. It's a shared count. But in terms of what I call how many did it own, remember in a bond, carbon had 1 electron, H had 1 electron, they teamed up. The carbon originally owned 1 here, it originally owned 1 there, and originally owned 1 here. I just say own. There's none here, so how many does that carbon own in terms of just what it brought to the dance? 3. Owns 3. How many is carbon supposed to own?
4.
We're always talking valence. 4. So it's missing 1. Or I can say should be 4. And this means it's missing 1, right? And if you're missing an electron, what's your charge going to be? Well, electron is negative. If you're missing a negative, it's going to make you positive. Okay? We put the charge on the atom here. Positive. Charge of the oxygen in that structure. How many does it own? It owns its lone pairs, 2, 4, 6. One of these, because the other one was originally owned by the carbon. So how many does the oxygen own? 7. How many is it supposed to own?
6.
Periodic table says 6. It's got an extra electron. So what's its charge? Negative 1. We don't have to show 1. A plus means plus 1, a negative means negative 1. Only rarely we will ever see things more than 1. Plus 2, minus 2, hardly ever. And if you ever see it, you need to say, hold on here, and just make sure everything's good. In Gen Chem ions, you can have plus 2, plus 3, all that stuff all the time. But the elements we're going to be seeing in organic, you know, these over here, plus 1, negative 1 is usually the max absolute value. Question?
Lone pair, when the lone pair transfers to make a bond with carbon, is that the same as electron transfer or no?
No, we're not doing any redox or anything. I would say when the lone pair moves in to make the bond, I would recommend transfer. Just trying to keep you out of trouble. Because if somebody hears transfer and then before you know it, you've gone the wrong way. Okay, so good structure. This has charge. But think about it a little bit. Oxygen is more electronegative. So we have dipole. These electrons are actually being pulled towards oxygen. As it's being pulled towards oxygen, the oxygen takes on negative charge. We'll talk more about that. All right? Build. So we ended up with a double bond. And, I mean, this is, if you ever show a structure, you're probably going to show this. It's the best one. And in this structure, we see 1 DUS. Okay? We'll talk about DUS in a little bit. Let's try the next one. HCN. How many valence electrons? I see 1, 4, and 5. What's that? Okay, let me make sure I said this. We showed a resonance arrow, yeah? Did we say those are resonance structures? Two we had here, resonance structures. Because what was the difference in those two structures? All we did is move electrons. And they were pi electrons. Once we learn what pi electrons are, you clarify that. Resonance structures, all you're doing is moving pi electrons. They're not isomers. It's really the same exact compound. All right? Just like if I move my arms here, I'm the same person. All right? ACN, 10 valence electrons. Structure. Let's say we bond the carbon and nitrogen together, yeah? Where do you want to put the H? Let's put it here. What next? Let's take care of this nitrogen. It's more electronegative. Let's make sure it's got an octet. What do you want to do here? 2, 4, 6, 8, 10 electrons? Nitrogen has an octet? Yeah. How about carbon? Doesn't have an octet. What are we going to do? Put some more electrons up here? No, we don't have any more. Maybe make a couple more bonds? No, we don't have any more. We've got to use what we got up here. This is the starting point. This is the approach. What do you want to do here? Hey, nitrogen, your friend carbon over here needs some electrons. You mind sharing? Okay. Let's move these in. What does that arrow mean? WDAM. Can you draw the result of that arrow movement? Yes. All we're doing is moving pi electrons. Resonant arrow. We now have HC. We now have what? Double bond. How many lone pairs on nitrogen? 2. Okay. There. Are we good now? Happy with that structure? Or are we... Nitrogen has an octet, 2, 4, 6, 8. Carbon does not. What do you want to do? These electrons move in here again. Let's do it again. What does that lead to? Triple bond, one lone pair left. How about that? Nitrogen have an octet, 2, 4, 6, 8, yes. Carbon have an octet, 2, 4, 6, 8, yes. Standard bonding for carbon, 4 bonds, no lone pair. Standard bonding for nitrogen, 3 bonds, 1 lone pair. It's all there. What's the best structure on the board? This one, that's what we pretty much said. 10 valence electrons, 2, 4, 6, 8, 10, yes. There you go. ACN, hydrogen cyanide, cyano group, nitrile group. Back over here. Didn't we say if it's not standard bonding, it's probably going to have a charge? Is that standard bonding for nitrogen?
No.
No, it's probably going to have a charge. What is the charge of that nitrogen? -2. Charge of the carbon. +2. Yes. How many does it own? It owns one of these and one of those. It owns 2 in that structure we drew. It's supposed to own 4. Missing 2. If you're missing 2 electrons, you're going to have a charge of +2. By the way, what's the net charge of HCN? It must be neutral because otherwise you can't. No charge if I don't tell you. All these are neutral because no charge is shown. The net charge of this is neutral. Charge here, nitrogen. Minus, carbon is plus here. Over there, everything is neutral because it's standard bonding. Okay? These are each resonance structures. This is the best. Which is the best of those two? One in the middle. It's closer to octets and there's less charge. One over on the far left is getting like, I'll ask you to sort of avoid. And remember, it's kind of extreme. This is the worst. I mean, that nitrogen pulls these electrons because it's more electronegative, but it ain't going to pull this much. Okay, we ended up with a triple bond, yeah, through our systematic approach. Formal charge and how to determine it, we've done that. Carbon with 5 bonds, not on this planet, but of course something like silicon just below carbon can have 5 bonds. Okay, there's a page about that. I'm not going to go over that page. All right, that's sort of extra information, but it's good information. Okay, a savvy student needs to be aware of that type of stuff. All right. Let's look at DUS. DUS is in one of the handouts. The other one, white handout, functional groups and DUS. For some reason, I think we should look at functional groups first. We alluded to the alcohol functional groups, the ether. Let's look at these here. Okay. Common arrangements of your atoms. Common arrangements have names called functional groups. And then functional groups have their own unique reactivity. And so the language of organic chemistry is organized around functional groups. We need to learn them. This table here, by the way, this comes from the Smith's textbook. I like to give you handouts from other textbooks. Okay? That way then you have your handout in your textbook and you have twice for the, okay? Make comparisons, different ways people present things. This top table are what? Table 3.1, what are these? Hydrocarbons, okay? Very important to read, understand what is being presented here. It's going to be hydrocarbons. Then you say, well, what's a hydrocarbon? Always, every step you go, you're asking, what is a hydrocarbon? It's a compound that contains what? Just hydrogen and carbon. Okay. If it contains a heteroatom, which is a non-carbon and non-H, it's going to be some other functional group called something else. Okay? Octane in gasoline is just a hydrocarbon. All right, different types of hydrocarbons though. Alkanes, all right? Basically saturated. Okay, I know why we covered the US first, because we need to start using terminology. I think I usually do cover the US first. We're not going to be able to cover functional groups today, probably. Please be looking at them, and we may go through this one next time. I can flip a coin what to do next. I think I do cover the US first because it's on the outline first. See, sometimes I can't remember, but the outline knows. All right. Let's do DUS. Okay, DUS, very important, very useful. Again, I don't want to show you things that are not useful. Very useful for dealing with structures. Very helpful. Determining DUS, which is called a degree of unsaturation. Some textbooks call it index of unsaturation or some variation of that. Basically, saturated, unsaturated are always going to be the terms there. You can determine DUS either from structure or formula. Let's first do it from structure. Okay, we just need to know a double bond is 1 DUS. A triple bond, that's my T, is 2 DUS. One ring is a DUS. One ring is 1 DUS. Okay, we just did a CN structure, yeah? How many DUS do you see? I see a triple bond. Okay, it's 2 DUS. There's no ring here. What is a DUS? Unsaturated. That refers to the number of hydrogens. If you have a C and an N there, you can actually have 5 hydrogens. For example, look at here. Just C and N, but 5, because this carbon can hold 3, and the nitrogen can hold 2. And that's the max, because you can't put any more hydrogens. The maximum number of hydrogens, you say the compound is saturated with hydrogens. Saturated. For the given heavy atoms. So, for C and an N, is that compound saturated with hydrogens? No, that's saturated. Well, how many are we missing compared to this? We're missing 4. Because that has 5 and it has 1. We're missing 4. Well, every 2 you're missing is a DUS. So since we're missing 4, how many DUS is it? 2. Well, that's what you already know because we said a triple bond's a DUS. I'm sorry, triple bond is 2 DUS. All right? We say this compound is unsaturated, because it doesn't have the maximum number of H's, but we say this compound is saturated. It has 0 degrees of unsaturation. It's saturated with H's. Okay, this here, it's an alkene. Then I think, well, we should have covered the functional groups first, because now I'm calling this an alkene. They go hand in hand. How many DUS do you see? Double bond is 1. How about over here? 0, because I don't see a double, a triple, or a ring. Also, for 2 carbons, the maximum is 6 H's. It's saturated with H's. But once we start talking that, I'm really doing formula. And below, I will talk that language. Right here, we're talking structure. Question?
The first example, the nitrogen with the lone pair, is the reason why that lone pair can't be a hydrogen because of nitrogen standard bonding?
Yes.
Okay.
We could put an H there, but then it would be charged.
Okay.
And then that sort of convolutes the DUS discussion at our level. Yes. Yeah, you could have an H there, but it wouldn't be typical, etc. So. Okay, how about this compound? How many DUS? We see a ring. Okay, a ring. Okay, it's not going to be a circle, but it's a closed. But it can be boom, boom, boom. All right? 4-membered ring. Enclosed, called a ring. I mean, what size ring is this? 3-carbon ring. All right? Well, that's a DUS. On the other hand, how about this? That's 3 carbons in a ring. This is 3 carbons, not in a ring. And notice, that has 6 H's, but this one has how many? 8. The maximum number of H's for 3 carbons is 8. We'll see that below. That only has 6. It's missing 2. Since it's missing 2, how many DUS? 1. But you already knew that because we see a ring, and I told you a ring is 1 DUS. See, the reason this is missing 2 H's is because essentially, if we take these 2 carbons and bond them together, we have to get rid of 2 H's to do that. Okay, ibuprofen. It got hole punched over there. It's on the back page of your syllabus. It's just this. This coming off is saturated. There's no pi bonds. Okay? And we haven't started talking about pi bonds yet. Doesn't it say pi bonds at the top somewhere? Yes. Really, each pi bond is 1 DUS. But a triple bond has 2 pi bonds. So that's why a triple bond is 2. But we'll get there. Ibuprofen. There's nothing out here. How many DUS do you see?
5.
5. I see 4 double bonds, 4 pi bonds. I see 4 pi bonds and 1 ring. 5. Okay? Formula. Hydrocarbons. We've already said this. We've already alluded to this. Maximum number of H's, that is saturation, is calculated by 2N plus 2 formula, where N is the number of carbons. If you have 5 carbons, how many do you need to be saturated? Well, it's 2N plus 2. You put 5N as N, 10 plus 2, 12. 5 carbons would need 12 H's to be saturated. Thus, a formula C5H12, you know that that's saturated. This is very powerful. For example, can a compound with this formula have a double bond? No. Because we know it's saturated, so no double bonds. Can a compound with this formula have a ring? No. This is some of the power of understanding what DUS can do for you. What about C5H10? How many DUS would be here?
1.
How do we do this? Well, what's the maximum for 5?
12.
12. 2N plus 2 is 12. We only have 10. Every 2 you're missing is 1 DUS. How many are we missing from max? Missing 2, so how many DUS? 1. It's explained there, but that's it. Okay? You can do it from structure or formula. What about when heteroatoms are present, non-carbons? Same as above, except halogen counts as an H, nitrogen subtracts an H, oxygen you just ignore. For example, Prozac has this formula. How many DUS in this formula? What do we do? What do we do with a halogen? Counts as an H. So the halogen, we can get rid of it and change this 18 to what, a 21? So that counts as H's. What does nitrogen do? Subtract. We can get rid of that and takes us down to 20. What do you do with oxygen? It's ignored. So the presence of that turns it into this, which I wrote here. That's what I mean by this. Now we do our standard. What's maximum for C17? 2N plus 2?
36.
36. How many are we missing? Missing 16 because we only got 20 after we manipulated for the heavy atoms. So if we're missing 20, how many DUS? I'm sorry, we're missing how many?
16.
Missing 16, so DUS is 8. Yeah? Structure of Prozac is on the syllabus handout. Let's look at structure. Over here. Here you go. Do you see the ADUS? How many double bonds? 5 bonds. 6. How many rings? 2. 6, 2 is 8. There you go. Right? One of my first worksheets in the workbook, there's lots of drugs and questions. One of the questions is, how many DUS does each drug have? What's the formula of each drug? Okay? Lots of questions on that one page, the drug page. Let's see, functional groups we'll be doing maybe first thing next time. Looks like we're ready to start with Roman numeral 3 there. We mentioned resonance. Please be looking ahead. We'll start hybridization next time. Okay. You need to be reading about hybridization. Okay, guys. Have a good day, and see some of you this afternoon.